Okay, let's get started. So, in summary, last time we looked at one proof of showing the error between sort of discretized Langevin dynamics, which is Langevin Monte Carlo, and the continuous time version. Okay, and essentially it's an optimization style proof where we sort of propagated a coupling forward in time, showed error bounds, and sort of propagated this forward. This is one way of doing it. So today I'm going to do the same result with different assumptions. So the assumptions needed were that the underlying density was both strongly convex and smooth. So and then we got a bound saying that if you want an epsilon accurate solution, then in terms of the Wasserstein-2 distance between the terminal distribution of the LMC and the stationary distribution of the LD. If you want it less than epsilon, then the number of iterations you need is essentially scales as 1 by epsilon square. Okay, there's a law, and it's linear in dimension. There's other log factors which I'm sort of just not worrying about right now. All right, so this is round one. This proof critically used both strong convexity and smoothness for two different pieces of it. The second proof is going to not use strong convexity, but then you'll get a different result. You will get deviation between these two, which will expand over time. Okay, right? I mean, that's the number of iterations. The reason you got sort of the deviations did not increase over time is because the strong convexity means that you would exponentially, the Langevin dynamics would exponentially fast converge to the invariant distribution. So it's essentially pulling things back, essentially. Okay. But if you don't have that, then there's a different style of proof. Okay. So this is Girsanov theorem approach for this proof. It's taken from again Chewy's book, log concave sampling, which actually this is the paper where this thing is from, which is Dalalyan and Sibakov's paper in sparse regression learning by aggregation Langevin Monte Carlo. But I'm basically taking it from this book, which is sort of talking about this paper. Okay. Also, the HD part is from Oxendal's book. So let's recap for a few minutes Girsanov theorem. Okay. So remember Girsanov's theorem? It just 2 classes back. We said that suppose you are an SDE with a drift of beta and driven by some Brownian motion, then you can write this as a different with a different drift, a different Brownian motion. So instead of beta, we can go to a different drift field. Okay, but this one is no longer a Brownian motion; it's some other process under. So this is under some measure P. This is a Brownian motion under a different measure Q. So you're changing the underlying measure, and there's a Radon-Nikodym derivative or the change in measure. You can characterize dq by dp using some martingale. It's an exponential martingale. So specifically, if you want to go from B to some other drift field A, then the martingale that's needed to twist the measure is this one. It is define U this way, and then it's it's e to the minus integral 0 to t u of s bs minus half u square ds. This writing it this way, it's not clear. This is a martingale. Which did I tell you? Did I give it as already as a homework problem at some point, or have you done it or not yet? Okay, yeah. There are a bunch of these kinds of things. Last time I sort of mentioned a few bookkeeping things which I skipped. So I'll put all that together as the next homework problem so that you can sort of get comfortable with these things. Okay. So summary is that from going from beta to alpha, okay, you can twist the measure, and that's going to cost you a certain amount. This is the change in measure. This is the dq by dp, which is the change in measure. This is a Radon-Nikodym derivative. Then YT has these two representations. Okay, right? We have done all this stuff before. I'm just sort of quickly summarizing. So this is used in many settings. The way we are going to use this, so let me pull this together. So there's a measure. So I'm interested in the trajectory from 0 to capital T. Okay. PT is the measure on path space. QT is the other measure. Okay. again over the entire path space. But for any fixed time t, you get the marginal distribution, meaning P sub t of any set A. A is a set in Rd. Is this measure is a measure over C0t Rd. Okay, is this capital P capital T is over the entire trajectory space. Okay. But I can look at the density at any point in time by just marginalizing it. Essentially, just marginalizing this over the trajectory or just marginalizing a single time slope. That's all. Okay. So this is the density. And let us assume that the Brownian motion is the same dimension as the ambient dimension. Remember, in the Girsanov, it was general. You could have a different dimensional Brownian motion. There's a matrix which could be tall and thin or whatever driving the process. Let's keep everything the same dimension. X, B, everything is in the same D. Okay. And let's also assume that the covariance is not a generic matrix. It's just a constant times identity matrix diagonal. Okay. So it's essentially, that means for every dimension is just driven by independently by the C. The C which we use for Langevin dynamics was √2, for example. Okay. Okay. In this setting, what does the Girsanov say? It says that if you, so there was ut times sigma t, this matrix was there. I can get rid of that and make this a constant. Okay. Then the ut function, which is the simply the difference between the two drifts scaled by c. Okay. And the key corollary is the following. If your drift changes from beta to alpha, then at any time t, the KL divergence between the density under Qt is under this, P is this. So you're looking at two densities, and you want to see how the density evolution differs. Then the density, the KL divergence is given by the following. Okay. You notice on this side, there's a capital T, here is a little t. Okay. The reason is that this is independent of t. This bound is true for any t. In fact, it's true for any joint distribution. The actual statement is true for this. It's sorry.
So capital Q and the expectation is the twisted measure.
Yes.
And that corresponds to P or to Q on the left? I just don't remember what you had said, because you pointed that Q is, okay, so Q is okay. So the right-hand side is also not symmetric.
Well, this is a square, right? I can just turn this around.
No, because it's expectation.
Yes, because KL divergence is not symmetric. KL is always with respect to the first measure. So the real statement is this, okay? That, let me start from the end and come back here, okay? This is equality. So let's actually, instead of the inequality, you can see this. So you could think about the KL in the path space. There are two measures of omega fp and omega fq. Forget about any point in time t. Look at the divergence between qt and pt. Okay, that's exactly equal to this. That's what we're going to prove. And data processing inequality says that, well, if this is true, then for any finite dimensional subsets of it, it will be, the KL divergence will just be smaller. Okay. So that's what, since we are only caring about the marginals, we've just written the marginal version. But if you ever needed to understand something about the joints at time t1 and t2 simultaneously, the same bound holds. That's what I'm trying to say. Does it make sense what I'm saying?
Yes, I'm trying to remember what the capital T subscript on Q is when we twist.
Capital T, can you repeat the question?
In the expectation we have Q, capital Q subscript capital T.
Correct. What is that? Let's go back. So this is the basic original process we started with some base measure P.
Right.
This, you can write this sample pathwise as this part by looking at the alpha minus beta, in this case, because sigma is constant, B hat is nothing but BT plus some difference in beta minus alpha. This is clearly not a Brownian motion under P.
Yes.
But it does become, that's what Girsanov says, it does become a Brownian motion under Q, where Q is defined as the following. It's the dq by dp is m, where m is this.
I'm still Is about the capital T. Why don't we have why don't we need to twist as a function of little t?
You're twisting the entire, because what is the probability space here? Okay, let's go back and no, this is good. So let's go to the last page. Give me a second. Let's draw a picture. Okay, here. This is your probability triplet up here. So this is the omega you have chosen. This omega leads to a whole trajectory. So that's what capital PT is, the measure up there. What is little qt? This is here 0 to t.
Okay.
I can fix a time little t here and then look at what is this cylinder set. This omega can be thought of a trajectory mapping, or it can be thought of as an infinite collection of mappings to each point. Okay. Yes. Do you see what I'm now? You see. So this measure here is qt. The density here is a little qt. It's at a fixed time. It's a so this object. Let me go back here. This object is C0t RD valued. It's a whole trajectory which is RD valued. Whereas this object here is just in RD. It is just a is this okay? Good. All right. So the claim is that the KL divergence is bounded by just the, if you look at the twisted measure, and it's just the average squared distance between these two drifts integrated over the trajectory, and the expectation is taken with respect to twisted measure. That's basically a corollary of Girsanov theorem. Yes.
EP and QT are actually measures over trajectory.
Yes.
Okay. So then when you say integral of expectation of some quantity with the QT.
Yeah.
But then YS is at a single.
Yes, because once you specify the joint distribution, you can always. So if I ask you, let's forget the infinite dimensions. Suppose I have a distribution, let's call it R, over a pair of random variables, X comma Y. I can still ask what is the expected value of X with respect to the R distribution. It just it automatically means the marginal at that point in time.
Right. Okay. So then that expectation can be the expectation over QS, like on QS.
Yes, it could. It will marginalize to just Q little s, little q little s at that point. Okay, but this is a path thing. You can just write it this way. This is also fine. Okay, so let's go to the proof. The first step is the data processing inequality. The KL divergence, if I look at it at any one point in time, it's smaller than the whole joint trajectory. Okay, that's all. Okay, so now let's go to the KL of QTPT. Now we are in the path space itself. Okay, that is nothing but the expected value of QT of log the Radon-Nicotian derivative dQt by dPt, and which is empty. Okay, so this is what is a KL divergence. So let's try to compute this. Okay, what is MT is defined as this. Okay. So log of MT is just the exponent, which is in minus 0 to t, capital T, US of ys dbs, half integral 0 to capital T, US square of ys ds. So here, U is nothing but beta minus alpha by C. So we have just substituted beta minus alpha by C. Good so far? So very basic question. Is this equal to 0? Why? I disagree. So he says that the first integral is 0. You should be careful. What is the measure? BS is a martingale with Brownian motion with respect to which measure?
Oh, you're doing human.
Exactly. So that's why you should be careful here. There are two measures going on. So he's indeed correct that an Ito integral has 0 expectation because of martingale. That's what we have seen. But here, this is not a martingale because this is BS, but this is QT. If we had put PT here, what he said was indeed correct. Okay, this would be expected value of this part would be 0, but it's not. You look very confused. You have to. So B hat is B plus this. So it will not give 0. That residual will come back. Okay. This is exactly that. So this, and so two ways of fixing this. I could make this QT and I need to change this function. Or I could make this PT and put a radon nicotine here. But then that's a different function. I don't know how to deal with that. There'll be, the radon nicotine is e to the something. Okay. So you don't want to fix it that way. Okay. The way you want to fix it is BS, so dBT is dB hat t minus 1 over C bt of yt minus alpha t of yt. I'm just writing this in differential form. Does it make sense? Sorry?
Second.
Correct. Okay. And so, so if you substitute this back in there, so then what you're going to get is first this part, once it's dB hat of t here, that part will be 0 because expected with qt and b hat of t, this part goes away. But yes, well, it's not it's a standard integral of a random variable. Okay, then the second term is minus 1 over c of this. There's a 1 over c already. This multiplies to give c square. This negative and this multiplies to give a positive. So this part will become plus 1 over c square ds. But this will cancel with 1 over 2 c square to finally lead me to just 1. Okay. So do you see? Let me go through the steps once again. Okay. So dbs is replaced by db. So we need to go to b hat of t, and we know the relation between b hat and b. So substitute for dbs as using this expression. This part of when you put this here, that first part of the integral goes away because of martingale. The second part, this negative 1 over c times negative 1 over c gives one positive 1 over c square. The inside of the integral is beta minus alpha. But then the second part of it says negative 1 over 2 c square. Okay, sorry. One more thing I forgot to say. There is this negative, so the constant becomes positive 1 over c square, step 1. There is a vector beta minus alpha, which is multiply. So there's another vector, there is this beta minus alpha. So basically you'll get norm of beta minus alpha whole square. So that's, then this 1 over c square minus 1 over 2 c square gives me 1 over 2 c square. So that's what you get up. And now I can push this expectation all the way inside. Okay. And that's all there is to it. Okay. So the proof is just going through the definition and realizing the martingale property with respect to the correct measure. That's all. Good so far? So this is almost immediate. Now you see why Girsanov's theorem is useful. It tells us how things will change when drift change. So now let's use this to actually do LMC discretization. Okay. So this is the second proof, which is the following. So the underlying density is pi star. It is proportional e to the minus v. So the Langevin dynamics is dxt is minus grad v of xt dt plus root 2 dbt. There's a continuous time evolution. The Langevin Monte Carlo is discretized at every time at discrete time step k plus 1 h. It's h is the discrete time step. It's equal to k, whatever the value was at time kh minus the time interval times just a fixed gradient. So you're just going at constant slope between intervals of time h. And the Brownian motion difference is just a Gaussian of 0h. This is LMC. As we discussed last time, we'll embed this in continuous time again. And the way we are going to do this is the following. At every discrete time step, at times of, so we'll take 0 to t, and we'll assume t is some integer multiple of h. Okay. Otherwise, we don't deal with the corner effects. So at every one of these time steps of h interval, okay, this is embedded at every one of these time steps. Okay, and between that, we need to somehow come up with an interpolation so that we get back into continuous time. And the interpolation is the following. At any point in time t, it is look at the previous discrete time step, look at the value. From then on, look at the gradient at that previous time step and do a linear it's just linear in time. Okay. So in any interval from, so let's call this t by h times h, that's this thing, and this is the next one. Okay, these are the two signs. So let's look at any particular time here, then you're just linearly interpolating between those two. Okay, that's all this is doing. And the Brownian motion is led to, at this point it was fixed, it's just left to evolve as is. So bt minus that. Okay, that's all the interpolation is. It's a very simple interpolation. At any of those discrete times, it's the same. Drift is linear, Brownian is not. It's just led to evolve whatever it wants. And then the theorem statement is the following. So this time, we'll just assume smoothness. We will not assume strong convexity. Okay. So the grad V is just beta Lipschitz. And now at any time, the Langevin Monte Carlo at any time is at any time t equals kh, the measure is mu kh. Pi t is the law of the Langevin dynamics. And we start with initial condition x0 is some initial distribution mu 0. Then if h is chosen small enough, the following, and at the terminal time is some n iterations, so of time h, then the KL between the terminal distributions mu t and pi t is given by the following expression. We'll break this down in a second, but first observation before we even say look at these terms. This is expanding in time, okay? Because we are not assuming exponentially fast mixing of the alpha strong convexity previously was used to show that if I want an epsilon error, then I will get something, I was using the fact that Langevin dynamics exponentially fast converges to this thing, looked at the discretization, use a strong convexity, as well as the smoothness to actually control the errors, and said that if I choose a step size small enough, and for any fixed terminal time t, if I want an epsilon error, then it gave me a schedule of how to choose my step size so that I can get essentially the number of steps needed was 1 by epsilon squared times dimension times log blah, blah, blah. That's what we saw last time. This is a very different form of a result. Okay. Yes. No, this is not, we are not assuming V is conic. This is a general statement. Okay. At this point, V is just smooth. Okay. It's not good. So therefore, you can't say what you can say is the errors will grow with time, but this is how it will grow with time. Okay. So there's at every step, look at how this gradient is, the gradient of V. There's a gradient square. There's some expectation of that. So that makes sense. That's the slope of some function. Okay. And so it should accumulate with n. Okay. As n increases, number of steps increases, that error increases. Each one is weighted by h cube. We'll see why that comes out. Plus, there's a terminal one which depends on h times t. So that's what we are going to prove. But then it doesn't say anything about, okay, so what, right? Can you say something more concrete? Well, now suppose in further that you assume that the gradient V is beta Lipschitz and pi star has an LSI, okay, which effectively is, it's strongly convex. This is the strong convexity implies this LSI. But yeah, we suppose that this is also somehow you have shown that pi star has some LSI. Okay. Then, this is what we should look at as an analog of the previous result with the Wasserstein coupling. Then we can indeed get things back. You can put things back in and show that if you want a total variation distance of epsilon, then the number of steps requires scales as d by epsilon square. These constants are different, the log terms are different, but essentially it's the d by epsilon square times something else. So a similar flavor of result.
So LS, just intuitively, LSI just means that I star has some concentration, or what is it?
Very formally, all that LSI, okay, there are multiple statements. One, we could go through the Carré-Duchamp. LSI says that gamma 2 is greater than or equal to C times gamma 1, whatever that may mean, the algebraic condition. That's equivalent to fast mixing. The KL so if you look at a Markov process, which this essentially means the following. Intuitively, the way you should think about it is, I look at the. Let's go to the Poincare. Okay, Poincare says how's the variance decay. Okay, look at variance, initial variance. It should go down, and the rate at which it goes down is e to the minus alpha t. Okay, that's the Poincare, and alpha would be the Poincare constant. The LSI would be the same for the KL. Specifically, yeah. Okay. The so if I choose F as a radon Nicodim, then the entropy is nothing but the KL divergence. Okay, so the LSI basically says that the entropy decreases exponentially in time, which is a fast con. Does this make sense? It's essentially how fast does the Markov process converge to the stationary distribution. And if it's alpha LS, if it's 1 by alpha LSI, that means it converges exponentially fast independent of dimension, with the parameter being alpha. That's the important thing. So, but alpha could be a dimension dependent thing, whatever it is. If you show me an LSI of 1 by root d, then that's basically what the rate of convergence will become. It is LSI controls two things. One is the mixing of the Markov process, but it's also about concentrations. You can look at it as a concentration story, right? If I want to get fast concentration, this would be the concentration parameter. And that machinery was the following, that you have a measure pi star and you want to show concentrations for it. You make up a Markov process, some generator L associated with it, for which this pi star happens to be the invariant measure. So you have got L comma pi star. And suppose for that L and this pi star, you're able to show a log Sobolev inequality of this form. Okay. Then that implies alpha is a concentration parameter, and C is 1 over C is a concentration parameter, and 1 over C is also the rate of convergence parameter. It's one condition is, suppose that the distribution was the form e to the minus v star, where v was a strongly convex function, then the strong convexity parameter becomes the LSI parameter.
Where did the integral of gradient norm squared? That's only.
I'll come to the proof.
That's only for one kind of process. This is more general than that.
Which
I think I should be bounded by integral of norm gradient squared.
LSI.
Is the entropy of f squared less than or equal to?
Yeah. Second, I'm not sure I understand your question, so let me go. So this is the LSI theorem, right? 1 and 2 are equivalent to each other.
I guess I thought it was normally stated as entropy of f squared is less than or equal to.
You're doing the Poincare, the Luxor. Let's go to the Poincare.
That's not Luxor.
So the Poincare was the variance is less than or equal to the C times Dirichlet form implies fast convergence. The LSI is this, the entropy. If you want to get an F, maybe you're talking about the Gaussian LSI. Okay, let's see. Maybe that's what you're. Yes, maybe you're thinking about the Gaussian LSI. Then in which case, let's look at that. This.
Yeah.
Okay, for the Gaussian, then you get this. Essentially, the special case of the Gaussian LSI, you get entropy of F square less than or equal to the Dirichlet form of F. But all this is asking if you can show a relation between either entropy and Dirichlet form or variance and a certain Dirichlet form, then you get exponentially fast mixing. Okay, and that constant is the LSI or the point in the point whatever in the Poincare is a Poincare constant. Here is a log Sobolev constant. So, yeah, is that does it? So, intuitively, this is not quite correct, but intuitively, in corollary, if pi star has a 1 by alpha LSI, you should think of that as V is strongly convex. That's not true. That's not a one-to-one correspondence, but essentially, especially if alpha is independent of dimension, then all this is basically saying is you go back to the setting of the first thing. So you got your Langevin dynamics converges exponentially fast. You get that as well. So you can put whatever the previous result along with this additional statement to get back something like this. So the Girsanov statement is interesting because it breaks it up into two parts. Just what does just smoothness give you? And then you can bring in strong convexity if you have it and sort of do the other corollary. This machinery is used in a lot of papers. So that's why I want to go through this proof as well for the same problem. I didn't talk about what the proof is, and so now we'll come back and go through the proof. Is the statements clear though at this point? Mhm.
Empty is an R1, right?
Empty is scalar.
Empty is scale. So what exactly when you're writing the form of, could you just go to the form of empty?
Girsanov?
Yeah, what the expression for empty?
Good. Let's go back.
Yeah.
So what is this?
Yeah,
This,
like an inner product.
yes, last time I was,
And
that is the notation. And this is,
okay, I just want to.
okay, this is what I mean by this. So in this notation, when you take vectors, U is a vector, okay? So when you write vector, Brownian motion also a vector in RD. So when we write this, we mean the inner product. I think the Girsanov notes have been much more explicit. I just copied this over here just in summary, but there I've actually written all the notation out. Okay, so we have set up the discretization, and this is the theorem statement. So let's actually see this. Okay, so we have a Brownian motion under some probability plus omega f p. So that's the Brownian motion here. So if you look at the Langevin dynamics, under pt, you have dxt is minus grad v of xt dt plus root 2 bt. With respect to the same Brownian motion, we have the embedded Langevin Monte Carlo. X tilde of t is x tilde th by at every time h, 2h, 3h, and so on, it's x tilde. And then the drift is a straight line, piecewise linear interpolation between those points. The Brownian motion is evolving as a Brownian motion, anchored at each one of these times, kh. So in differential form, you get dx tilde t is minus grad v x tilde fixed. This is not changing. Okay, so note that in the Langevin dynamics, at the same time, here it's not. It depends on some past time. Okay, till you cross the next h, then it depends on that point in time and it's constant. and then, but the Brownian motion part is exactly the same. Okay, so that's essentially the difference. The drifts are different in these two things. Okay. So, which is essentially what you want in the differential form. The drift field itself is changing between interpolation times with the LD. In the Langevin Monte Carlo, you fix the drift field, you keep the same drift up to this point, then change it to something else, keep the same drift for a while, then change it to something else, and so on. Whereas in the LD, it's actually continuously evolving, the drift itself over those points in time. Okay, all right. So then what does, so now I want to understand little qt and pt. So the KL divergence, first for capital QT, okay, the of course less than or equal to, but let's just write equality when we actually have equality. So the KL divergence between QT and PT is look at the entire trajectory with respect to the QT measure, look at the difference in the two drift fields, the integral square dt. This is exactly what it was beta t minus alpha t. Now we have just said what these two things are. Okay. Now this is Lipschitz. We are using is beta Lipschitz. So I can put, there's a square here. So there's a beta square that pops out. Okay. And it's the difference between xt and some slightly older version. How much has xt changed over an interval from t by h times h to t? Okay. So, or some small interval of time. Well, now what is the okay, good. This is the random variable with respect to the q measure. So what is the drift field which this xt is using? Exactly, the alpha, which is the discretized version. Good. So that means this difference is nothing but, look at the discretized version, the gradient square, times the time difference. That's what this is. This is proportional to time difference square times the drift square. And the Brownian motion is the usual Brownian motion. Over this interval of time, it is just d times the time interval. That's all the Brownian motion variances, okay, under the Q measure. So, and that's basically it. At this point, oh, there's a typo here. Okay. I want to see what is xt minus xt. So what is this? So like, right, this is what the equation is. Because I've done the other measure. It's under the Q measure, not under the P measure. So under the Q measure, xt is evolving with the alpha drift and the Brownian motion. Okay. And so under the alpha drift, how much has from time t to t by h? So what is this difference? It is, I've gotten some particular time here, let's say it's of the time kh, and then there's some time t, and this is k plus 1h. So I'm looking at what has happened over this interval of time. This is t, this is kh. Okay, so how much is things going to change over this point, this interval of time? Well, the drift is going to move it, which is t minus that time interval, t by h to t. It's going, and the slope of that is this. It's constant at that point in time. Okay, so that's one part. And then I'll just use triangle inequality, right? It's sum of two terms. The Brownian motion part of it will give me, now you know the Brownian motion's variance is nothing but it's just linear in time and linear in dimension. So it's d times this difference. That's all. Okay. Now you need to do this integral. And to do this, you need to break up this integral 0 to capital T into little bits of h, 0 to h, h to 2h, 2h to 3h, and break every piece. Okay, because for each one, this term is going to be different. But you can see that roughly this part is going to give me, okay, let's just do a hand wavy calculation. This is order h square. Okay, because that's what the interval time is. And there are let's see. So this is order h square So this integral of that from 0 to h. So if I look at this for a small interval from 0 to h, that integral, that will give me h cubed by 3, 0 to h. So it,
Times h, right? Don't I?
yeah. That time, the integral of h square time, you're right, but it's not h cubed, it's h cubed by 3. That's all
I
I'm
mean,
trying to say.
T minus T over h times h.
That's right. Which is that's why I'm getting a h cube. This is order h. T minus T by h is order h because it's in a block of, look at a block of time h. T by h is at the beginning of that block. By the time T goes a whole h ahead, then the block shifts to the next block. Okay. Let's draw
I'm just
attention.
saying it shouldn't it be floor of T over h times h?
I'm just asking, what is this term going to become?
It needs to be T minus floor of TH times H. There needs to be a.
Oh.
Yeah,
Is that okay? Yes. Thank you. Thanks.
and then is it inequality? This is equality in the top?
I don't know.
Uh,
It doesn't matter. There's made the Brownian motion triangle. There's a sum of those two terms. Maybe something becomes zero mean when I multiply that of independence, but I don't care. Okay, this is true. I'll just use triangle inequality and be done with it. Okay. There are two drift. There's a drift term and a diffusion term. We can just put up or above. Okay, this is fine. Okay. What I was trying to argue is this term is going to give me a h cube. That's clear now, okay? And then for each one of those things, it's whatever the drift was at those times, at the beginning time, because that's what these things are. I'm looking at times 0, h, 2h, 3h, and so on. Okay. So you'll get a summation over each block of this thing. This is the expectation. This one evaluated at times kh. And this integral will give me h cube. That's all. Okay. That's where this term is coming from. And then this Brownian motion term, again, this is going to be h integrated over integral 0 to h. So it's going to give me a h square term. There are n of those pieces. So it's d h square, d is still there. There's a h square and an n. The rest of it you can figure out. There's a beta square by 4. This 2 will cancel because the integral of h is h square by 2. That will cancel a 2 and all that stuff. But essentially, it's just bookkeeping now of all these little integrals. Okay, I'm just trying to convince you that the scaling is all correct. The constants you can just figure out. And that's essentially the Girsanov proof. Okay. So once you have Girsanov CM, this is very straight. There's very little to be done. You just look at the two drifts and just take care of figure out how much those drifts deviate with respect to the Q measure. That's all there is to it. Okay. What we want though is we want to start from this and somehow, if indeed we have additional properties, that the pi star is an attractor, meaning you have alpha 1 by alpha LSI, or equivalently you have strong convexity. They're not equivalent. I shouldn't say equivalently. Though in my head it's these are sort of similar. It's not. They're different things. In that case, then what do you get? Well, then we will actually get something like the Wasserstein coupling proof, which is that the number of steps. If you want an epsilon accurate solution, then it tells you that you need d by epsilon square number of steps, and h should be chosen appropriately. So all that I've sort of brushed under the carpet. So this theta tilde will have some h buried somewhere inside it. Okay, you can choose h so that you can get a 1 by epsilon square accurate solution. And the proof, okay, where is the LSI used in the proof? I'm not going to discuss the proof, but I'll tell you roughly where it comes from. Okay. So KL does not have a triangle inequality because it's not symmetric, but total variation does. So you need to somehow go to a total variation distance by root KL. Pinsker's inequality relates KL divergence and total variation distance. So go to a total variation distance where you can get a triangle inequality. Okay, first. Once you can, then you need to sort of segue between something else. Okay. So first point is that now the LSI assumption is used. The LSI assumption is used that the KL divergence between the stationary distribution and the distribution at time NH of the true Langevin dynamics is small. Okay, because it's moving it's coming down exponentially fast. If you want to get a small error, then you wait for a certain amount of time, which depends on the LSI parameter, and at that point, the actual the stationary distribution versus just the standard LD where it has come to at some point in time at time NH is small. So now that's your anchor. You got that point. Now you got some sort of a triangle inequality because of total variation distance, and then you can use our previous result to go between pi NH and mu NH, which is the Langevin Monte Carlo, and patch everything together. Okay, I'm not going to go through the details. You can read it in the book. All right. So at this point, we have about 20 minutes left. Okay, good. I'll sit.
The same way we had like Poincaré for like sort of variance, and we had like LSI for like KL, those things. Is there like some other sort of inequalities that we can use to use this machinery, but for Wasserstein convergence?
What do you want to go to Wasserstein instead of KL?
I want to do Wasserstein.
But there's HWI inequality. So
there's another machine.
Okay. Well, so you're asking what's the connection between KL divergence, total variation distance, and the Wasserstein 2 distance?
No, I'm asking.
Because once you have that, I can just throw that inequality. Exactly. So that's called the HWI inequality. It basically says something. Yes, you get one-sided, but then something else gives you I can pull up the notes later. So I have a whole lecture in my advanced probability class on all these connections between Wasserstein 1, Wasserstein 2, KL, and total variation. Many of them are one-sided, but I think you can get to a Wasserstein 2 using some of these kinds of things. But offhand, I don't remember exactly what to do. Okay, yes.
The upper one which you got for the scale between mu T and pi T, it is unbounded, right? Because it's actually like linear in it. Like if you look at the second term. Like beta.
Yes.
So then how can you use that for getting like an epsilon?
So you should be carefully choosing H and T so that that bound will be fine. For any epsilon and T, it's still bounded. There's a H cube term in this business too. So you have to choose H. You fix a T such that first you fix a T. So T doesn't go too far because of this control. Okay, because of the alpha fast mixing. So, okay, intuitively what is going on? You know that things are unbounded as T goes to infinity. Okay, but alpha LSI means that mu NH and pi star are really close to each other really quickly. Okay, that's what fast. Okay, does it make sense? That's a qualitative statement. Second statement. The second statement is pi star and pi. Pi star and pi NH will be close to each other, and the n is very small. The T, NH is T. I'll think of NH as T. That T is not too big. Okay, that T is not too big because pi T is becoming very close to pi star very quickly. Okay, and that's enough control you have to pull everything together. I think that's what you're asking. Yeah. Okay. Okay. So this is the Girsanov machinery. And if you see the papers in the last few years in cold IC, the usual places on all these, when people are studying either DDPM or Langevin dynamics, this is sort of the underlying machinery that this is used all over the place. So now at least when you read those papers, you know what is going on. Okay, what's the trick that they're building? There are more details depending on what kind of dynamics. With DDPM, there's other things which are also happening, right? The drift is not exactly just minus grad log VT, something else is happening. But still, this is the kind of machinery that is used. So I could, at this point, do the DDPM proof using this machinery. Okay. But I'm not going to. I'm going to do a third machinery for DDPM proof so that you get access to one more sort of toolbox. Okay. So the paper sort of for looking at such bounds for DDPM, remember 3 lectures back when we motivated this whole discretization bound, we did the elbow and said that, hey, this looks like a discretized, we did a continuous time evolution of DDPM from which by construction, we got exactly correct sampling at the right time, at time 0. And then we did some discrete version with an elbow, and then we interpreted that as a discretized DDPM. Okay, so now you can ask what is the error because of using that discretization with respect to the true density which you'd like to sample from. So we'd like to do exactly what we did now, not with Langevin dynamics and LMC, but DDPM and discretized DDPM. Okay, we'd like to go through that connection, and we can do using indeed Girsanov. We can do this kind of a proof. Okay, you should be careful, and so that's one machinery. There are several interesting papers that build on that. Okay. So some of the important papers in this are by Sitan Chen, Sino Chiwi, and others. By sampling is as easy as learning the score. So this is then Holden Lee et al.'s paper, which is convergence for score-based generative modeling with polynomial complexity. Then this paper by Benton, De Bertoli, Arnaud Doucet, and colleagues. Delignadis, I guess, yeah. How do you pronounce it? Delignadis, correct? Okay, pretty close. Okay, I'm looking at Constantine here to make sure that I got the pronunciation right. Okay, yes. So these are all really cool papers. Okay, so I would strongly suggest that you look through this. This is a different machinery from what we are going to talk about, but it builds on the kinds of things we talked about previously, that style of thing. Instead, I'm going to use this very recent paper, which was just posted on arXiv, I think in August this year. I like this proof a lot. So, and because it again shows a different way of thinking about it. So that's basically what I'm going to present here. Maybe in July or something. It was the last few months it was posted. It's by Galen Reeves and Henry Pfister. It's called Information Theoretic Proofs for Discrete for Diffusion Sampling. And this builds on something called the IMMSE, very well-known paper by Dongning Guo, Shlomo Shoma, and Sergio Verdu from 2007. Yeah. I'll show the connections in a bit, but this is really what I'm following for this particular node, though there are many other ways of doing this. Okay, so let's start. Today, I'm not going to finish this proof today. This is for next class. Since I've sort of finished this particular thing early, I'll sort of set things up and tell you what's going on. And next time we'll come back and revisit this. So let us consider the following dynamic, discrete time dynamic here. Zk is Zk minus 1 plus some step size delta k times some function, which could be time varying of Zk minus 1 plus some independent noise. It starts on 0. So this is just a dynamic which is just the setup. Okay. How is this connected to DDPM? First, let's think about that. Okay. If you choose f sub k is the conditional expectation of some underlying random variable x0 given Zk minus 1. Okay. Then you can start thinking about this as a DDPM-like equation. Why? What does DDPM do? The discretized DDPM looks at the score and then takes that score value and moves forward with that as the drift till the next time step, recomputes the score at that point, fixes that score and goes to the next time step and so on. Correct? That's what. But what is score? Score is affine in the conditional expectation. That's what Tweedy's formula says. So Zk plus delta k fk of Zk minus 1 is some of, if f was the conditional expectation, that is an affine transformation of score. Okay, so by choosing delta k appropriately, you can get DDPM-like things by just choosing the appropriate function fk. But this is a more general dynamic we have just said. Suppose you had a dynamic of this form, and W tilde k is some Gaussian. It's a zero mean identity covariance. That's all this is. So now, hopefully, you can see the connection between this equation and DDPM. Okay, is it clear? No, no issues. Okay. This is clearly a Markov process because it's a discrete time Markov process. This is in RD, okay? And this thing depends only on some independent randomness, some deterministic function of previous state. So it's clearly a Markov process. Good. Now we are going to define a different process, yk. Okay? Yk is defined as the following. Let x0 be from some ground truth distribution mu star. Okay? This is what you want to sample from. Yk is yk minus 1 plus delta k xk plus root delta k times some Gaussian. It's not at all clear this Markov. There's this x0 sitting at every time step. It is same x0. It's not that we are regenerating x0. You draw a sample of x0, freeze it, and then define yk this way. Okay? This is a weird process. Yes. Y0 is 0. I'm just going to assume y. I'm going to initialize it. Y0 is 0, and y hat is just Gaussian. Okay, this is my dynamic. So initially, right? So y0 is 0, y1 is some delta 1 x0 plus root delta 1 w Gaussian. It is some blur Gaussian. I mean, it's some smoothing of x0. Okay, because x0 is the sample, it's fixed, and then you're just smoothing it using a Gaussian. Y2 is y1 plus, so y1 plus this, which means y1 plus delta 2 x0, but this is not an independent x0, it's the same x0 as before, plus an independent Gaussian, which means it is some other scaling of that x0 plus some linear combination of Gaussian, independent Gaussians, which means that's again a Gaussian with some other parameter. In particular, therefore, this dynamic is exactly equal to this. You can write yk as some tk. Tk is the sum of delta i's, whatever those step sizes are, okay, times x0 plus wk, where wk is a Gaussian with mean 0 and variance tk. Because it's why is it variance tk? Because it adds root of delta 1 plus root of delta 2 plus root of delta 3 and all that stuff. So each one, the variance, the square, if that's the standard deviation, the variance will be the sum of these things square, which will mean delta 1 plus delta 2 plus up to delta k. Okay. So summary, we have two processes. The first process is zk, which is defined this way. And the fk you want to keep in mind is this. Okay, that's what your fk. You're going to think of fk as this function. Okay, there's a conditional expectation.
It's not a Markov.
I don't know what it is yet. It doesn't look like it's a Markov process because it is just I'm taking the same quantity. So if you once you write it this way, it's very clear what is going on. It is just I'm just taking the same point and adding different amount of noise. That's all is going on. Okay, it's scaled and re-added some amount of noise. Okay, but yk is very clear what is going to happen. If I choose, so for intuition, let's say delta I is delta k is 1 over k. Okay, then tk is order 1. Actually, it's log n, but I'm going to ignore all the logs. Okay, let's ignore logs for a while. Tk is order 1, and wk.
Figures, root K, sort of root K.
Is zero mean variance tk. So as k becomes really large, okay, this should be order log. If k is large, this is order log n. X0 has a X0 signal is boosted up by log n, and the noise variance is log n, which means the noise standard deviation is root log n. Okay, good. Let's. So I will use the 1 by k because that log n is actually important. Okay, so let's look at this yn for k equal to n for n large. Let's just see what this looks like. Okay, for n large, tk is roughly log n. Wk is a zero mean Gaussian of variance log n, which means the standard deviation is root log n. But xk, x0 is boosted by multiplied by log n. That means the signal is sitting around log n, and the perturbation around it is root log n. It is small, which means yn is roughly x0 because the signal is much stronger than the noise. Noise magnitude, not variance. Does it make sense what I'm saying? Okay. Which means yn is roughly x0. So if we prove that zk and yk are close for k large, then you're in business. That means that yk, that what are we doing with this dynamic? This dynamic is asking, what we'd like is to show that zn for n large is roughly x0. Okay, right? That's because we want a sample from x0, but what we have access to is just the conditional expectation of x0 given z. Okay, that's your score. Is it making sense? Before I start doing any of the math, I want to sort of give a big picture view of what is going on here. Okay, so zk is essentially discretized DDPM by choosing fk appropriately, and you want to show that. So normally think of it as backward in time. This is moving forward in time, just iteration. For k large, you want to argue that Zn is roughly x0. That's what you want to do. Is it making sense? Are you okay with what I've roughly? No, not clear. Okay, let's go back to Zn. What we want to show is that Zn for n large is x0. Why? Let's ask, why do you want to show that? What is x0? X0 is the ground truth distribution. I want a sample of an image x0. Okay, and so I want Zn to look like x, at least in distribution, look like x0. So this dynamic, I want to look at dynamic 1 and argue that that is looking like, for n large, Zn looks like x0. Fine. Step 1. Step 2. Now we have a completely different dynamic. It's not a Markov process. We first sample an x0 and keep it. So of course, that x0 is exactly what you want. And define yk in this form. Yk is tk x0 plus wk. So for k large, for k is order n, okay, we can argue that tk is log n, roughly. Okay, and this one is a Gaussian of zero mean and variance log n. If the variance is log n, its standard deviation is root log n. So this whole term looks like log n times something plus root log n. For n large, this root log n is small compared to this. So that means yk is some scaled version of x0. So I can take yk and divide by tk and get back x0. So what I'd like to argue is this yk by tk and zk are close. Okay, that's what we want to argue. Then we are done.
FK is going to be this.
Yes. In fact, fk could be the score. This is a very general analysis. If it's not the score, we'll see what happens. Okay. So, what we want to so roughly to make what I said, I was very hand wavy about it. In specifically, we'll see next time that yk by tk is actually exactly a sample, which is the ground truth convolved with a noise. Okay, which is of 1 by tk variance. If tk is log n, then it's small variance. Okay, it is almost mu star. It is not quite mu star, but it's almost mu star. Okay. So this is the key theorem. I'm just going to state it, and then next time we will start going into it. Okay. Let's look at the KL divergence of the y sequence and the z sequence. Okay. Then the claim is the following. That KL divergence is upper bounded by the following. Look at the trace of the covariance matrix of X0. So the data distribution. So it's D. If you think that the data, let's say the ground truth is some D-dimensional distribution, under some nice conditions, it should be order D. Okay, there's amount, because on every coordinate, the amount of energy should be order 1, hopefully. So that means that trace of covariance of X0 is an order D quantity. Okay, times some step size delta max. Okay, we can choose whatever the step size is. Delta max is max of delta 1, delta 2 up to delta n. Okay, you can choose whatever step size you want. You can control that. Plus the second term. At every step, you're going to accumulate an error. That's the difference between what your FK is and the conditional expectation. So if you actually use FK equal to the conditional expectation, you wipe it out completely. But if you have a noisy score, it tells you what's going to happen. Okay, it's telling you all sorts of other things, this expression. Okay, if you don't have a true score, if you have a bad estimate of your score, well, you put it in and that's how the error is going to accumulate. Okay, second part. And that's it. That's their main theorem. And the proof is a very, very different style of proof from what we have seen before. Okay? In particular, therefore, if you choose the FK correctly as the conditional expectation, then this thing combines in this iteration, this thing, not this one, sorry. This one combines to basically become the score. Because the score is, you remember there's a linear term and there's a conditional expectation term. That's what grad log, what was, when 3D's formula said that that's what score should be. Okay, so you have essentially got discretized DDPM. Second point to note here. So suppose now the guarantee you want is the following. I want to use DDPM such that I know that I can't exactly sample from the true distribution mu star, but I'm willing to fudge it a little bit. I want a smooth version of it, which is a Gaussian with zero mean and epsilon variance. So we choose whatever epsilon. Okay, epsilon is small, it's slightly, you smooth it just a little bit. Okay, so suppose this is my goal. I want to sample from this distribution. Okay. Then you can use this and show that, well, if you choose the step size as epsilon by n, okay, then you're going to get that the KL divergence between y and z, okay, is going to be 1 by 2n epsilon times the trace of the covariance. So this could be order D. So you'll get this. So now it tells you how to choose the step size to actually control the divergence. Okay. Second, it tells you more interesting things. So this gives me a 1 over n convergence. So people in the literature have thought about, if I don't do exactly the score, but do some perturbation of the score, can I get faster than 1 over n convergence? And there's literature on that. Okay. So this is basically about 3D's formula gives you a score and it converges, but maybe I don't want to exactly use the score. Okay. If you choose FK such that instead of it deterministically returning this, it returns this plus some random variable. Okay, where this is carefully controlled. Then in particular, it returns a value where moments match the rth moments. Instead of just a conditional expectation of x0 given y, it x0 to the power r given y. Okay, then you can get 1 over n to the r convergence. You can get all these kinds of things using this dynamic. Okay. So I really think this is a very beautiful proof, which is why I wanted to present this. Next class, we will actually talk through what the ideas are inside this proof, okay, and get to it. But at least now you see where we are going with this business. Okay, I'll stop at this point. We'll start with next class. Again, I'm going to start from 0 and go through all this. Okay, thank you.